Today we are going to start with some examples of subspace questions. Last time we talked about that, and today we are going to do a few more examples. Then we are going to go talk about null spaces. And if we have time, we'll have additional topics on linear combinations. But first, let's see. On the topic of subspaces, we looked at problem 6 last time. So let's take a look at another one. I change it a little bit so that we are specific. Let's say V is R3. So in all of these problems, we start with one large space, linear space, where you have all these vectors, you have addition of the vectors, you have multiplication by scalars and such. So those are the background in which we operate. Then we go and take a chunk of this space. In this particular example, it says let's look at the set S, which is made out of any number. The second component of the vector is twice whatever the first component was, and the third component is 3 times whatever the first component was. So X is just a number. So this problem is somewhat similar to a specific example of problem 7 on 3-4. Question is S closed under addition? Next question, is it closed under multiplication? Final question is S a subspace? We said subspaces are the special sets which you have closure under addition, closure under multiplication. We gave a visual description of what these things are. The subspaces are in essence a flat shape. The shape passes through the origin, and the shape is complete. It doesn't have anything missing on that flat shape. So for example, in 3 dimension, we said these are the examples of subspaces. The origin by itself is a subspace. Any line through origin is a subspace. What else was a subspace? Any plane through origin is a subspace. So these were the subspaces. We had the origin. We had any line through origin. And we had any plane, again, through origin. And the entire space, which is, of course, again, through origin. So in a 3-dimensional space, we have these type of subspaces. What is important about a subspace as opposed to a subset? A set could have any shape you want. Any kind of a curve there would be, any collection of points would be a subset. Okay, anything you pick is a subset. Subspace, there is that property of linearity to it, and the fact that it passes through the origin and it's complete. So it could be an origin, it could be the origin, it could be a line through the origin, it could be a plane through origin, or it could be the entire space. In higher dimensions, we cannot visualize easily, but a similar phenomenon occurs. Now, if we look at this, what we are emphasizing is that if you have these two properties, then you have that visual look over there. Now let's come here and take a look at this. This is set of vectors in R3. What kind of vectors are there? They have a special look. They have some first component, whatever we want to take. The second one is double of the first, and the third one is triple the first. Would such a thing be one of these type of entities? What do you think? You can have two approaches. One is try to visualize what the situation is going to be, and the other one is try to check these properties, if these properties hold in this case. So closure under addition means if I pick one of these guys, here's one of them, and another one of these guys, so another one of them is going to have perhaps a different first component. So I might start with, say, y. If the first one is y, what's the second one? 2y. And the third one? 3y. If I add two of these things, do I get something that still has that kind of a look to it? Well, let's just add them. The first component is x plus y. The second component is 2x plus 2y. The third component is 3x plus 3y. Is this a member of that kind of a set? Yes. Why? Because the second one is really, what is it, the second one? If you simplify it, second one is indeed twice the first one, and third one is 3 times the first one. So to say something is a member of such a set, we use this notation. If you remember from set theory from high school, so this is a member of S. This is a member of S. I just picked them so. After this simplification, I noticed that this is also a member of set S, because all that is required to be a member is that this is double of that and this is triple of that. Is it closed under multiplication? Well, if I take x, 2x, 3x, some member of the set S, and multiply it by some scalar. Let's choose our scalar to be some number t. What do I get? Tx, T2x, T3x. Well, what is this thing? First, I look at it as Tx. Second one is twice the first component. Third one is 3 times the first component. So we chose this as a member of S. This one, I look at it because of the look of these coefficients. This is also a member of S. So conclusion is S member of is S closed under addition? Answer was yes. Answer was yes. Is S a subspace? And the answer to that is yes. Anytime these two are yeses, so is this. If it fails any of these tests, that is not a subspace either. Now, if you have taken some algebra 3 or some calculus 3, you over there, or at the end of calculus 2 actually, you notice that this description is a description of a certain line in a 3-dimensional space. For every step in the x direction, you are taking 2 steps in the y direction and 3 steps in the z direction. It's some line that goes in the space, like one of these red lines that I have drawn here. So that would have been another way of looking at the same problem. Now, problem 7 really is asking you a little bit more general, which could be looking a little bit more confusing, but it's essentially the same thing. It says our background space is some n-dimensional space. The chunk that I am considering is a set of vectors in that space that have the following look. Okay, so instead of R3 that we considered in this example, in problem 7, really what it's looking at is Rn, which means you have n component. It could be 4-dimensional, 5-dimensional, or 100-dimensional space. The vector that you are considering is having just as many components as you had over there. So if this was R100, 100-dimensional space, this would be 1, 2, 3, all the way to 100, and still X is just a number. Same question, is S closed? And exact same question approach applies. Is it closed under multiplication? Same story, even though we have no picture to draw. So conclusion from this is that it is what? The S is a subspace. So we have to get this terminology straight. Subspace, special word we use to indicate something with these properties, not to be confused with a subset, which is anything goes type of a situation. You know, whatever you pick there is all fine and dandy. As a matter of contrast, so I start first with a simple example. This is like 7 prime, kind of looking like problem 7 is 8 prime, kind of looking like problem 8. Same story. So we start with V, is 3-dimensional space, and S. This is set of vectors. The first component is X, second component is X squared. Let me make the problem is even a little bit easier so that we don't slave over irrelevant algebra. Let's make it even smaller. So I took a 2-dimensional space, R2. A chunk of it is set of points whose coordinates are, first one arbitrary, second one square of whatever this guy was, X, real number. Same question. All of these 24 problems is same questions. Is S closed under addition? Well, you have to kind of have a sense about this problem. Essentially, you have to jump the gun first and then load it. You have to decide visually from your impression what it is, and then try to choose a strategy to establish what you are saying. What do you think? Is it closed under addition? When you say no, you have to give me an example. Remember that when you say okay. Exactly. It's a common mistake in college algebra and such. Let's see what is involved here. What is involved is if you pick one element, one arbitrary element, and another arbitrary element, and add them. So question is it closed under addition? Our guess was no. We go ahead and check. Okay, first component is x plus y. Second component is x squared plus y squared. This one I chose to be a member of S. This one I chose to be a member of S. And here's a question. Is this guy member of S? Well, who is member of S? Member of S are the guys where the second component is square of the first component. If it were true that this was a square of that, that is, if it were true that x squared plus y squared were really square of x plus y, if that was the case, then this guy would have been a member of S. But is this true? No, this is obviously not true. Common mistake to say these guys are equal. It isn't. Who is missing from the left-hand side? This guy needed 2xy. So this is not closed under addition. Automatically, we already know that S is what is not a subspace. I don't need to go check the second criterion for making a decision. I already know, but most of these problems take you through 3 questions. You already answered 2. Is S closed under multiplication? And that means the scalar multiplication. That means if I have an element of S chosen multiplied by some number t, well, what am I going to get? going to get tx and tx squared. Again, here's a matter of knowing your algebra well. Is the second component square of the first one? Is tx squared square of tx? No, because remember, this squaring is happening first, multiplication happens later. T is not being squared here, so this does not match. So is it closed under multiplication? The answer to that one is also no. We already gave a negative answer to that question anyway, but here it completes the picture. Some of these problems turned out to be a tad bit more what do you say, less visual, or perhaps higher dimensional. Like problem 11 says, let's consider a background space M33. The book uses M with subscript M in M is to be set of n by m matrices. Okay, set of all matrices of a certain size. So here we are looking at 3 by 3 matrices. So if I want to write this, it's set of all things looking like this, where all the ingredients are some arbitrary numbers, a all the way through I are real numbers. So that's our background space. How many pieces go into that space? 9 pieces are there. So now we are kind of jumping ahead of ourselves. This is a 9-dimensional space. It takes 9 data points to specify any single member of that space. Okay, set of all 3 by 3 matrices. Now this is a vector space by itself, meaning you can take 2 of these matrices and add them. You get another one of the matrices in that space. You can take one of these matrices and multiply by a scalar. You get another one of those matrices. And then you have all those properties like commutativity of addition and associativity of addition and all of those things. So this is one big linear space. What is it that we want? We want to take a chunk of it. What chunk we are considering? We say take a set S, which is made out of all matrices A such that, so there's an art to reading this thing. What is it that you're talking about? So this A here means one of these guys. Now I have to describe what does this, what's so special about this guy. Set of those matrices with this property. What does this mean to you? A is equal to AT. The other word for matrices that have these properties is what? A is, if somebody is equal, no. It is what? It is equal to its transpose. We had a word for such things that they are equal to their own transpose. No. Give me an example of something that's equal to its own transpose, like 3, 5, 7. What goes on this column here? 5, 7. So transpose meant take the rows and turn it into a column. Yeah, symmetric. Very good. So if it was 8, 9, this guy has to be 9, this is whatever it is. So transpose meant symmetric. These guys have to be the same across the main diagonal. This is the main diagonal. On the main diagonal, you can have anything you want. Whatever is across this has to match, like this diagonal was a mirror or something that is a symmetric image of itself. So A is symmetric. Same question. Is S closed under addition? So you have to kind of get used to answering these things by kind of manipulating the ideas in your head and coming up with that answer first, and then when you're writing it down, you can be a bit more formal about it and explain it all in details, but really it happens in your head first before you write it down. S closed under addition. What does that mean? I'll have to kind of translate it into words to make sure that just simply symmetric matrices, yeah. So what is the idea? Is it closed under addition? So let's take somebody, member of this set, which means symmetric. Let's take another person, which is member of this set, which means that is also symmetric. If I add two such things, what do I get? Well, I just get sum of the two matrices. The question is, this sum that I have is the sum member of that set. If I have two symmetric matrices and I add them, let's make a symmetric matrix. What do you think? If I add two symmetric matrices, do I get another symmetric matrix? Let's say if A, B, C, then this has to be B and C. If this is D, if this is E, who is here? E. And who is here? Whatever you want, say F. So suppose this is your matrix A. Matrix B, let's write it with X, Y, Z's. X, Y, Z, who's going to be here? Y, Z, say S, R. This has to be what? R, T. So this is another symmetric matrix. So suppose this is A, this is B. The question is, when I add them, is it still going to look like this? Meaning that the element here and an element there are going to match each other. Element here and element there, would they match each other? And what do you think? Of course, so if this is A plus X, we don't have any problem on the diagonal. Whatever you have there doesn't make any difference. The question is, off diagonal, if this, you have B plus Y here, you also have B plus Y here. So if these are symmetric, that is guaranteed to be symmetric. If you have C plus Z here, you have C plus Z here. D plus S, I don't care about that. E plus R, and then again E plus R. And F and T, again on diagonal, we don't care. Is it closed under addition? The answer is yes. What does that mean? In sum of two symmetric matrices of same size, is again another is a symmetric matrix. So this guy is a member of S. You have to kind of run through the whole thing in your head first. The picture has to come out in your mind there first. Then you translate it into writing, write it in detail, say, okay, if you don't believe me, here it is. Here are all the details. How about is S closed under scalar multiplication? Yes. How do you multiplication? How do you translate it into a English phrase? English phrase, I mean, like that. You take a symmetric matrix, multiply it by something, like double it, triple it, or something. The entries are still symmetric. So if I take T, multiply it by A, B, C, B, C, D, E, E, F, this look is going to be preserved. This is TA, TB, here's again TB, here's a TC, here's TC. TD, we don't care. TEs are the same. TF, so the answer to this thing is yes. So that tells us that set of symmetric matrices. Now notice how abstract the whole thing is. We are operating inside of a 9-dimensional space. We never visualize anything that's 9-dimensional. But that doesn't bother us. Inside this gigantic space, we have a kind of a slice. That slice is occupied by symmetric matrices. Kind of hard to kind of visualize such a thing, but inside of that 9-dimensional space, there is a slice that is occupied by this symmetric matrices. That slice is just like one of these things that we saw here. It's like it's flat, it goes through origin, it's complete without holes or anything, it just spans all over the place. It's portion of the space, not the whole thing. So it's a spatial subset of that 9-dimensional space. It's a set of 3 by 3 symmetric matrices. So you kind of have to get used to that language more so than anything else. Once again, the algebra you go through is trivial compared to what you see in calculus. The issue is not to do any addition or subtraction. The issue is understanding the concept, what is involved here. Okay, so that was one such example. Let's take another example. Just the language is different. V is equal to C of A and B. Who is that? This is a notation like many other notations. This is problem 15. Many other notations in mathematics, the one might not have seen it. This stands for continuous functions on, and this is where the function is defined, on interval A through B. Okay, so it's just a shorthand for that expression. What do you mean continuous? To make it simple, continuous means what? If it is AB, it means when you're drawing it, you don't take your hand off the page. You can't draw it in a single stroke, as opposed to what? Discontinuous means you have to take your hand off to draw it. Okay, there's a little bit of oversimplification, but the whole story is explained at the beginning of calculus 1. We don't want to go through that detail. Okay, then it says let's take a cut of this space. Okay, all these guys are there. I'm going to take a small chunk of it. Say S is the set of. Now you tell me, what does this mean? I have a F here. Who is the F here? You remember? Say it again. A function, yes. Okay, so this is a chunk of that space. Who are these guys? These were functions. So any chunk we take, it's going to be made out of functions. So F is a function. F is a function with what property? With property that F of A is 0. So can you visually describe, or can you verbally describe to me what kind of a subset are we focusing on? This function that I drew has to have a special property to belong to this group. What is the property that we expect? This is A, here's B. Here, say I want to draw it. Where should I start? Is this good? No. On the line. Okay, so this is, as usual, cryptic in mathematics, but that's how we talk there. Starting point is 0, so it means whatever function you drew, better start right on the x-axis. That's all. It says, okay, of all these continuous functions, only look at the ones that start right off the x-axis at the left point. Question. Okay, are these guys gonna make a, well, let's go step by step. Question 1. Is S closed under addition? Notice things have changed quite a bit. All the previous examples that we had, the space that we were looking at was either R2 or R3 or maybe R4 or something. But this is, how many dimensions does this one have? Let's see, ask you. This is a set of functions how much freedom do you have in wiggling your hand to make a function here? Quite a bit. How many functions can you draw? I mean, can you peg it down to anything? No, it's really infinity. It's bigger infinity than really what infinities you are used to. There is an order of infinities, and this one is beyond the just a regular 1, 2, 3, 4 going all the way to infinity, and there are infinities past that infinity. This is the one after the first infinity is like the second infinity or something like that. So the space that we are looking at is not even something that we could visualize. It's not that kind of entity. It's not like R2, R3 and such, but that doesn't again bother us. We don't care how big that space is. We are taking a chunk of that space. We cannot even visualize this one, but we can ask some question about it. Is that closed under addition? Yes. Yeah. If you add two functions that start off of x-axis, the sum also starts off of the x-axis. The answer is simply yes. Because if you add f and g, if f was a member of S and g was a member of S, then what is f of a? Well, first you say, I have two functions. I add them. So that's another function. Is the sum member of the set? So, okay, go calculate it at the left, see what you get. At the left, whatever the left value of f was has to be added to the left value of g. Well, this was 0 and this was 0, so the total is 0. That tells us that this is a member of a set S. So it passes the membership test. If two of them are a member, sum is a member, and so on. 2 is S closed under multiplication. If a function starts at 0, if you double it, what happens? Still starts at 0. So that is not a big surprise there. And as such, we say S is a subspace. So it gets to have that ordinary title of, notice again, this is an infinite dimensional space, and its infinity is even beyond our regular infinity. This is a slice of that space. This one is also infinite dimensional. But what we can assert about it is that in some sense it is flat. It doesn't curve around or something. Whatever that thing is, it has same flatness property that we expect out of lines and planes and such things. Very good question. So if I add here like 2, 3, what happens? You add 2 of them, then it goes 4 or 6. So you're talking about things that are different. So there is something special about this type. Okay, let me leave a few of these things for you, and then let's pick of this group 22. V is equal to P2. So I'm explaining really what these notations stand for, and if you read the text, you'll get a better explanation. And what does P2 stand for? P2 is, P stands for polynomial. Of order or degree up to 2. Not that it is 2, but it's up to 2. What is the degree of a polynomial? Like if the highest power. So this is highest power. Give me an example of some members of P2. 5x squared plus 7x plus 11. This is a member. So is x squared minus 19. But we say up to 2. So if you had just x, like say 7x plus 20, that's fine. You don't even have to have any x's in it, so you can have like 13. What is the degree of this one? This is degree of this guy is 0. This one degree is 1. This one degree is 2. So V equal to P2, this is our background space. This is where like we have big pile of stuff there. All the P2s go into that room. P2 by itself is a vector space, meaning if you take two of these things and add them, you get one more of these things. If you take one of them and multiply by number, you get another creature just looking like the stuff that you started with. Occasionally, two of them could cancel each other out and such, but the degree never goes up. It could go down, but never goes up. Like if you have this one and you have another member like minus x squared plus, say, 11x plus 17, when you add them, x squares go away, but all that you are left with is some x's and some numbers. So you could add degree 2's and end up with a degree 1. But that is also in that room. That is also in that set. So this collection is a vector space. Now we say, let's go ahead and take a chunk of this. This chunk S is the polynomials of the following form: 1 plus something times x plus something times x squared. A and B are numbers. Okay, once again, what is V? Any polynomial of degree up to 2 falls inside of this container. We are picking these guys out. Question: is S closed under addition? Yes or no? Yes. If I add two such things, do I get another one of these guys?
You get the same power. You just get the same degree, just higher numbers.
Look carefully. No, look carefully. Do you? Something about it doesn't work. What is it that doesn't work? If I add two of these guys, do I get another one of these guys? Look, this is 1 plus a. Let's see, what are we talking about? Here, 1 plus ax plus bx squared. This is one member of set S. Give me another example. Another member of set S. 1 plus cx plus say dx squared. C and D could be anything. If I add them, what do I get? 2. So what is striking about that? Yeah, it's very similar. Again, we are nothing like integration by parts or anything. It's just you're adding 1 and 1, and notice it's no longer 1. That's all. It left the set it was in because the set that it is defined started with 1. That's a kind of a clue. Any number other than 0 is a problematic number. It just kicks you out of that set as soon as you add them. The answer is no. Under multiplication, so if I take one of these things and multiply, what happens? So t times 1 plus ax plus bx squared. Yeah, you don't have to get 1. If t is anything other than 1, this pattern is going to be messed up. Because, well, if this is not 1, you are no longer a member of the set S. So if t was 2, this doesn't have to be a member of the set S. The answer here is no, and either of these things tell me that this subset is not a subspace. Okay, so once again, I emphasize you do all of these problems. Let's see, have something new here today. We want to talk about null space. A major preoccupation of linear algebra is to solve equations like this. Okay, the holy grail of linear algebra is to solve ax equal to b. It just takes a whole course to do that. In Algebra 1 back in high school, it says, oh, x is b divided by a. But now, this is a matrix. that is some vector, and you are trying to catch this vector x that fits this description. So we try to approach this thing little by little because the problem is complicated enough. We try to start with some things that are a little bit less out of control than this one is. To control the problem, we can try to simplify the right hand side. Say, okay, what if I want to solve ax equal to 0? Okay, never mind just some arbitrary right hand side. Let's start with something easy that we can chew on. So okay, what if the right hand side were 0? What's the solution of that? Say it again. Oh, well, well, interestingly enough, that doesn't have to be the case. I mean, if x were 0, we will be all done. But what happens in linear algebra is that the product of two things or a bunch of things could be 0 without any of them being 0. That is the so the multiplication that we are talking about here is not like a multiplication you had in basic algebra. For numbers, if you have product of a bunch of numbers is 0, well, then one of them has to be 0. You actually had a name for that. You call that zero factor property or something like that. That was the basic tenet of your life for the last 4 years perhaps. Any equation you solved, if a times b was equal to 0, either a was 0 or b was 0. But now we are turning the page and you want to say, well, that doesn't have to be the case, and that's going to be enough to occupy a whole chapter or such. The set of all possible x's here is called the null space. A null space of matrix A is the set of all x's such that when you multiply a by x, you do get 0. And that is not necessarily a trivial set or a small set or anything. It's not just a 0. Okay, our shorthand for this is going to be ns for null space. Ns of A is going to be shorthand for null space of A. Okay, let's go ahead and start by some examples to dispel this idea that x had to be 0. Let's start with A to be okay. We took some, it could be any kind of a matrix, no restriction at all with respect to anything. Let's start with that one. X is our vector. Remember, is made out of several components. So we have to have a list of as many things as it takes to do the actual multiplication. To have the compatibility for multiplication, we need few x's. Now, what does ax look like? Ax 1, 2, 3, 6 times x1, x2. Tell me what is the first element of the outside of the output vector. Just multiply. Is that right? Yeah, you just multiply like we have been multiplying stuff all along. So it's 1x1 if you wish and 2x2. That's the first entry. What's the second entry? 3x1 plus 6x2. Is that right? So that is our product. What we want, null space, is the set of such things such that the right hand side becomes 0. 0 means everybody is 0. So I want x1 plus 2x2 to be 0, and I want 3x1 plus 6x2 to be 0. So what does that lead to? It leads to a kind of equations that we have been working on since the beginning of the semester. Only thing that is special about it is that right hand side is just all zeros. Well, what is kind of striking about this equation? Like if you try to do Gaussian elimination to it, what happens? So if we used to do Gaussian elimination, we try to get rid of stuff here. You say what? Let's do Gaussian elimination. What happens here? Entire bottom row, that this is just triple of that. Is that right? So there isn't really any information here that wasn't there already. If I were to write this with the Gaussian elimination, minus 3 times first row added to the second row makes this thing entirely 0. So the only really independent equation here is this one. Whatever is true of this is going to be true of that one. Give me some example of solutions to this, such as what? x1 is equal to something, x2 equal to something. Like, okay, -2 and 1. Is that one acceptable answer? Give me another one. What if x2 was equal to 2? x1 will be -4. Now, suppose I go ahead and picture all of this thing. I consider this one my x1 axis, this one my x2 axis. What kind of a, if I take all these examples, 1 minus 2, where is that, if I want to plot it, which quadrant is it going to be in? 1 and -2 is here. 2 and -4, this is 2 and -4. If I take all such examples, 0, 0, of course, in another example. Somebody was saying minus half or something like the collection of all these answers is going to constitute what? If I keep finding more and more answers for all decimal possible values of x1 and x2, all of them together is going to form a straight line. Is that right? Which is a line with this equation, x1 plus 2x2 is equal to 0 is going to be some line. And what is important about it? Among all possible values of x1 and x2, the set that constitutes the null space of A is what kind of a space? Exactly, excellent. This is a subspace. The story today is that null space is a subspace. Let's not get lost in this terminology. This is a set of all answers of AX equal to 0. Subspace meant if I have one member and another member, if I add them, I get a third member. If I have one member and double it, I get another member. So subspace had that closure property. We are saying null space has those closure properties. Null space is a subspace. So we want to learn that. You want to do the exercises. Okay, try problems 25 through 40 for Monday. Do at least one of each type, and we are going to talk on that and then continue.